In this class, we learn about voltage regulation in power transformers. Why voltage regulation is required for any instrument? So, electrical equipments and appliances operate most effectively at their rated voltage. So, voltage actually should be within a particular limit. So, it is necessary that the output voltage of an instrument is within narrow limits when the magnitude and power factor of loads vary. Otherwise, voltage drop occurring in every section of the system, the equipment which is farthest from the substation would receive the lowest voltage. Of course, lowest voltage or highest voltage, it depends on the whether the load is leading or lagging, or capacitive or inductive. Normally, inductive load is assumed, so that's why here it is written the lowest voltage. But if lines are without load, then they behave like capacitors. So in that case, the leading current will go. Then the voltage at the farthest end will be higher than the input voltage. So therefore, voltage regulation is an important performance parameter of an instrument that determines the quality of electricity supplied to consumers. So voltage regulation of a transformer you might have studied in your previous courses. The voltage regulation is defined like this. Regulation is open circuit voltage minus load under voltage under loaded condition divided by open circuit voltage. Means no load voltage minus loaded voltage by no load voltage. This is in per unit. In percentage, simply you have to multiply this factor by 100. So that then you will get in percentage. So V2 is the secondary terminal voltage at a specific load. So regulation is dependent on the load also. And V2 OC is the secondary terminal voltage when the load is removed. So when the voltage is under the system is under no load. So this is the regulation. Means it indicates the drop, percentage drop or per unit drop from no load to full load. So this is what is regulation. And here the diagrams of transformer, simplified equivalent diagrams of transformer are given here. So these are two representations given here. Normally this shunt branch is neglected. So if it is neglected, you can see. So this is I1 is approximately equals to I2 dash. So here this is R equivalent is R1 plus R2 dash, X equivalent is X L1 plus X L2 dash. These are the resistive components and these are the leakage reactance of primary and secondary together. Here it is given, referred to, this is referred to primary side. And in that case, here the ideal transformer will be there, you can assume, because all the parameters are represented here. Actual practical parameters are represented here. Therefore, here at the end you can assume ideal transformer and then V2. So where AV2 you will get, A is the turns ratio, AV2 you will get, and the other side you will get simply V2. So V1 to V2. Similarly, if the shunt branch is neglected, you can simply see this series branch and then V2 dash and V1 relationship you can see. The Phasor diagram of that is given here. This is V2 dash plus this is V2 dash and then I2 if the load current is lagging by theta 2, then say V2 dash and V2 dash plus I2 R2 plus J I2 X2. So this is the phasor diagram. So you can see here the phasors I2R2 is parallel to I2. So I2R2 is drawn here. This is like this. And I2JX2 is perpendicular to I2 actually. So that's why this is perpendicular to this phase I2 phasor. So and you can see here, and it's the theta 2 angle, which is same as here. Here this angle is also theta 2 and this angle also theta 2. Then this AC, AB is simply I2R2 cos theta 2. That is A into I2R2 cos theta 2. It is given here. This is I2R2 cos theta 2. And then BC, this BC is simply DE sin theta 2, DE sin theta 2. This is EF, DE sin theta 2. Then which is equal to I2 X2 sin theta 2. So the difference actually, this OD, since the delta is very small, OD is approximated as OC, as you are already aware in previous classes. So the difference, the difference is simply AC is the difference actually. AC is the difference, means V1 minus V2 dash. See, now V1 is what actually, if you do not have any current in this, and that means in no load conditions, simply V1 is equal to V2 dash when no load condition, no load. So therefore the regulation formula becomes V1 minus V2 dash divided by V1 into 100 for percentage regulation. So here it is given here. The V1 can be estimated as OC, which is OC equals to OA plus AB plus BC. OA plus AB plus BC. So this is actually approximate. OD equals to this is OC. This is approximately equals to ODN. That's why this relationship has come. And the regulation is open circuit voltage minus V2 dash divided by V2 OC. Now V2 OC is simply equals to V1. So V1 is approximately equals to OD. OD na? Yes, OD. This is approximation actually. This OC is approximation. OD is exact only, OC is approximation. So the regulation formula turns out to be like this. This you already know. And similarly, in the previous case we have seen lagging power factor condition. In this case, leading power factor condition. Now this is theta. This angle is theta. This angle is theta 2. Theta 2. So similarly, again phasor diagram if you draw, this is I2R2 phasor, this is J I2X2 phasor, and V2 dash plus I2R2 plus J I2X2 will give us V1. Similarly, again using these triangles, we can simply show that this I2X2 sin theta 2 is this. So and I2R2 cos theta 2 is this. So the difference between this OD is again approximated as OC. That is equals to V1 equals to V2 OC, open circuit voltage. So this is what the approximation we do here. And with that, the difference between this V1 and V2 dash is simply equals to CA. So V2 OC minus V2 dash is equals to simply V1 minus V2 dash equals to OD minus OA is approximately equals to OC minus OA is approximately equals to CA, which is equals to this expression. I2 R2 cos theta 2 minus I2 X2 sin theta 2, I2 X2 sin theta 2, this voltage regulation using this formula. But remember, in this case, if regulation is negative, then it means that the voltage V1 is less than V2 dash, means the sending end voltage is less than the receiving end voltage, means at the receiving far end the voltage will be higher in magnitude. Ways to compensate reactive power for better voltage regulation. So due to inductive nature of loads, reactive power is drawn from the line. This leads to voltage fluctuations. To regulate the reactive power demand, methods exist such as, say, synchronous condenser, local, this is local, used for power factor correction, mainly used for power factor correction. And capacitor or reactor banks, this is also local. Excitation currented generators. So this is not done in practical, as this affects load in between actually. So excitation currented generators, will not be exercised. So capacitor and reactor banks also works locally. Synchronous condenser also locally. But online load tap changing transformer is a globally accepted method to compensate this voltage regulation. So now we will look into OLTC, online load tap changing transformer. So this is a typical diagram showing online load tap changing transformer here. So there are two arms here. So this is the connection actually, high voltage connection you can see. So here what will happen, we will be shorting a portion of the winding actually. We are taking connection from a particular what a tap. These are all taps, 1 2 3 4. You can, this just exaggeration shown completely here, but so many taps need not be there. So here how these connections are made. Actually, before there are two actually. So when before making the new connection, so it will not be broken. So one of the arm will move and then touch the other, touch the next tap, and after it gets connected, then only we will lift the other one. So always at least one of these arms, connecting arms, will be always connected to one of the taps. So there will not be any interruption, because current interruption is not good. So current can be diverted, but it cannot be interrupted. Interruption means it will lead to huge arc, and then there will be arc byproducts also. Not only that, then mechanical wear and tear will also be there. So therefore this is how it is done. So here some points are there. A 2-point contact system is used. I have already told, make and then break. First make and then break. So before breaking one arm, one connection, you have to make another connection, ensure another connection. So this taken at the middle point I will show you. And while doing the tap changing, how the voltage changes is of interest. So actually this voltage changes in a fashion, it looks like a flag. That is why these diagrams are called flag diagrams. Therefore, the phasor diagram need to be understood actually. There are two types of OLTC. One is buffer type OLTC and then other one is resistance type OLTC. So, in a transformer, please note that voltage per turn will always be same in a transformer, irrespective of primary or secondary. Voltage for one turn is constant. Now here, the buffer type OLTC is shown here. So there are, so this is transformer winding, high voltage winding. So various stages are shown here, case A, case B, case C, like this. 5 stages in which one complete transition from one tap to another tap is given here. So here first this is actually high voltage winding. This is high voltage winding. And the winding has several taps. You can see 1, 2, 2, 3, 3, 4, 4. These are all taps actually on winding. So where do you tap? For initially it is at 1, 1. So this is the tap connected. And there are two arms, you can see A and B. This A and B. Both arms are connected like this. So sorry, this diagram is downwards. The current is downwards only. I by 2, I by 2. So total current is I. This is the transmission line. This is the line, transmission line. Now, so this is a connection actually. Now this is connected. Now the voltage is at tap 1. Tap 1. So current is 50% this side, 50% this side. There is a buffer reactor here. This is buffer reactor. So this reactor, in this part, the current will be in this direction. In this portion, the current will be in this direction. So the MMF will oppose each other. So the net MMF is 0, near to 0 actually. We assume that net MMF is 0. So if MMF is 0, then the voltage drop across this or flux is 0, then the voltage drop across this reactor, buffer reactor is also 0. In that case, exactly whatever voltage is there at this tap, that V1 also appears on the transmission line V1. So this is how the connection is there initially. Now how do we move? We will discuss. Now before moving, so just let us draw the phasor diagram of this one actually. So this is the voltage phasor. Here the V1 is there, V1. And then load current, this transmission line current can be I. And I can be at any angle. Let us assume I to be lagging actually. You can do the same exercise for leading also. So this is the angle theta and this is current I. So this is the phasor diagram of this. There is no magnetization current in this because the currents I by 2 and I by 2 are equal and opposite, and there is no flux linking the coil. Therefore, there is no voltage across the coil also because 1 and 1 are at same potential. So therefore, there is no voltage across the coil also. Therefore, the magnetization current is also 0. So this is the phasor diagram for this position V1. Now this case A. Now let us come to case B. Case B. So now our objective is to move from tap 1 to tap 2. Means, we are increasing the voltage. So tap 1 to tap 2, the number of turns included in the winding are more. Therefore, the voltage will be more. I already told you that voltage per turn in a transformer is constant. So if we are increasing the number of turns, obviously the voltage will increase proportionately. So now we are moving to tap 2. So how to move this? So there are two arms, right? A and B. So these two arms, one of them we have to lift. So here in this case B figure, you can see arm A is lifted. So in this condition, how the currents and voltages will be, we have to see. So now here, the moment this arm A is lifted, now the half of the current which was flowing through A has to be diverted from B alone. So the entire current I will flow from in this direction only. So from B only. So then here XB is there. So therefore, now earlier what happened, half of the current was coming from this side, half of the current was coming from this side. Therefore, the buffer reactor had no flux because the flux of each portion will be opposing each other. So the buffer reactor had no flux. Now, but half of the portion is having no current because the A is lifted from the tap 1. So therefore, in this case, since entire current is flowing through half of the this reactor only, then suppose XB is the reactance of this, then there will be a drop corresponding to this one. So now the voltage of transmission line here is given by V1 minus J I full I into XB, whatever is the reactance XB. Now let us see what the reactance XB is. Now in this case, the phasor diagram I am writing here, the phasor diagram. I am taking that phasor a little bit down. So this is V, this is I, this is theta, that is load current. This is V1 position. Now V1 minus JXB. So this is I. JIXB is 90 degrees to this actually. So I have to draw a phasor which is 90 degrees to this current I. I am assuming that this is 90 degrees to this current actually. So this is the position somewhere here. The magnitude of this is I into XB. So JIXB, V1 minus JIXB. So this is position A, case A, and this is case B, the voltage at case B. So the voltage is given by V1 minus JIXB. So now this is the condition here in case B. This is how the phasor diagram will look like. And case C, you can see, in case of case C, what is case C actually? The A, which is lifted, is now touching the tap 2. So therefore, the currents and voltage situation is like this actually. Now again, the half of the current, nearly half of the current will shift to tap 2 and half of the current will shift to tap 1. So I by 2, here I by 2, and here I by 2 will flow, and apart from the circulation current. The circulation current is shown here with green arrows actually. This is circulation current, which is also superimposed on this. Therefore, the total current here is from tap A, I by 2 plus I M. The circulation current, let us give the symbol of M because it is magnetization current. And here I by 2 minus IM. So here it is indicated already. This is I by 2 plus IM and this is I by 2 minus IM. So total current in this is again I. Now the phasor diagram here corresponds to this actually. This is V1. This is case A, V1. V1, case A also, and this is our I, this is our I, which is at angle theta. Now, now the magnetization current is at 90 degrees to V1. This is V1 because V12 is the voltage that is appearing across the coil, V12. V12 is simply V2 minus V1. This voltage is appearing across this coil altogether from here to here. Therefore, the magnetization current is perpendicular to V12. Now V12 is in phase with V1 and V2 actually. So this all transformer windings, every winding of every turn is in phase with the total winding voltage actually. So V1 is in this phasor. So 90 degrees to it. So this is the phasor of magnetization current IM, which is circulating actually. Now let us see what is I by 2 minus IM and what is I by 2 plus IM. So this is actually I by 2, roughly here. This is I by 2. So I by 2 plus IM. So this phasor, I have to add phasors like this actually, just like vectors. So this is I by 2. This phasor is I by 2. This is I by 2 plus IM. And then I by 2 minus IM. This is I by 2 again. So I by 2 minus IM is like this actually. So like this. This is minus IM from I by 2 minus IM, I by 2 plus IM. This is minus IM, and here say, for example, this is, you can take this to outside also. It depends on theta actually. It depends on the value of the theta. This phasor I by 2 minus IM. So this is the typical phasor diagram of various currents here. Now the position of the voltage at this transmission line is how much? Actually V12 is V2 minus V1 is exactly distributed half, because this complete winding is symmetrical and we are tapping at the midpoint, exactly at the midpoint. So the voltage drop in this half is equal to this half. So the voltage at the midpoint is exactly equal to voltage half of the V12. So that will be here. So the node potential is between V1 and V2. So suppose V2 is here. Suppose V2 is here. Now we are getting exactly at the middle of this one. So this is position C. This is position C. And earlier position B we have identified. This is position B. Now this is position A, this is position B, and this is position C. So this is this also we can mathematically also we can prove that this is the positions, this thing. Then how to prove that? So this is V2. Say you can proceed from either V1 or V2. So in this case, V1, what is position C? V1 minus I by 2 I by 2, due to I by 2, here you have to understand one thing. The flux, half of the current is going through this winding, and half of the current is going to this winding, this I by 2. Total I is shared between these two parts. So similar to the case A, in the case A what happened, the fluxes are equal and opposite. They have cancelled out the flux, right? So therefore, due to I by 2, there will not be any drop in the windings. You have to understand this, because the other part of the I by 2 in the other winding will cancel this flux. So there will be no induced EMF in the windings. due to cancellation of the flux by other half. So there will be no drop due to I by 2. Now we have to consider this only Im only here. So in this case, minus of, actually, let me first write complete equation. V1 minus I by 2 minus Im into xb. This is j, because why is j is required? Because it is jxb is the impedance of that one, this one actually, jxb into I by 2 minus Im. So now this is 0, because current is not 0, its effect is 0. Now V1 plus j Im into xb is the voltage. This is the position C voltage. Now where is Im? So Im is here. J Im xb is in fact in phase with V. J Im xb is in phase with voltage. Now this magnitude, so here this magnitude is simply J Im xb. So we are getting V1 plus J Im xb. Similarly, if you come from V2 side, same can be shown to be V2 minus J Im xb. So between V1 and V2, you are exactly at middle. So this is Im xb at the top also, Im xb at the bottom also. So this is position 2 V2, this is position 1 V1, and this is position C is here, which is exactly on the midpoint of these two. So this is how the phasor diagram will be. Now next is case D. In this case, now again we are lifting B. So when we are lifting B, entire current is shifted to A only, and from tap 2 entire current is going through this one. Now here again this XB drop will be there, because there is no opposing flux here. From here there is no current, right? No current. Therefore there is no opposing flux. Therefore we are getting complete, here the voltage drop will be there. That is again V2 minus J, complete current I, into XB again. So the phasor diagram gets simply, here itself I will draw with a different color, just to indicate you where exactly the this case D voltage will be there. So it's exactly same phasor amount actually as case B actually. Case B and case D are similar, just except that this comes from V2 and earlier it came from V1. So this is D, position D. This voltage is exactly same as this V2 minus Ji into XB. Now you can see. Now after that, simply now when you lift in case E, what you are doing in case E, simply this B lifted, which was lifted, and it will be touching the this tap 2. And in this case E and case A are exactly similar, only that in case A it is 1 1, in case E it is 2 2. So exactly half of the current will be flowing. Sorry, this is in this direction, I by 2. So this is in this direction, I by 2. So both half of the currents will be going through the winding I, like this. So the phasor diagram in this case, simply both MMFs, this flux and this flux will oppose each other, and there will be no drop in the inductor, buffer inductor. There will be no drop. Exactly voltage V2 will appear at this V2. So this V2 is simply this Phasor diagram. Again, I am drawing here itself. This V2 is corresponds to case A. Now you see from where we have moved. Case A was here, case A was here, case B was here, case C we came again on the V phasor, case D is here, case E is here. Simply if you connect these two, this movement, you can see it appears like a flag. So that's why these diagrams are called flag diagrams. Now what is the use of these flag diagrams? Actually, we are interested in knowing the voltage between the lifted arm and the taps which are close to it. For example, consider case B. In the case B, now we are lifting arm A. Now, what is the potential between arm A and 1? Because when you are lifting, if the voltage is higher, there may be arc. And what is the voltage between A and approaching tap 2? That is also. So, voltage between these two and voltage between these two are of importance. Now, what is the voltage between these two? Here in the case B, you consider here an important thing is now only half of the winding the current is flowing. Will there be voltage drop? Voltage in this? There will be voltage because the flux lines will go through this winding. Flux lines. They will be linking this winding also. So even though there is no current in this portion, when you lift it, the moment you lift it, all these turns will have induced EMF exactly same as the EMF in this portion also. So the voltage will be, the double the voltage of this half winding. So what is the voltage of this half winding here? So now here the node voltage, when it is lifted, the potential of the node voltage is given by V1, because V1 is this one, entire current is going like this, V1 minus 2 times, because not half, 2 times I into XB. This is J we have to add somewhere, so I can add J here itself. This is because XB is associated with reactance, so V1 minus 2IXBJ. So where it will be actually the phasor. Now I draw with the green color in this. So V1 minus JIXB. So here this is actually double. So this is V1 minus 2 times JIXB. Now that is the voltage of arm A. This is the voltage of arm A. Now we are interested to find out what is the voltage difference between node 2 and arm A. So this is the voltage difference between node 2 and arm A. So V2 minus this thing. So this is the voltage difference between V2 and arm A. And what is the voltage difference between V1 and arm A? V1 and arm A is simply 2 times JIXB only. This phasor, this entire phasor is V1 minus 2JIXB, and this entire phasor from here V2 to this tip is the difference between voltage between node 2 and the lifted arm A. Similarly, where is the other case? Other case is case D. In case D, this B is lifted here. B is lifted. Then what is the potential of B? So exactly same way here, it is actually V2 minus, because again here half of the winding only will be having current, the other half doesn't have any current. So the flux is not being opposed. The flux will link entire winding. So therefore, whatever voltage appears across this half portion will also appear across this half portion. So therefore, the total voltage drop is V2 minus 2 times J into I into XB. So again, in this case, so you have to, if you use different colors, which color should I use? This color, let us use. So here, this phasor, again we have to extend this phasor by double. So exactly same. This tip is equals to V2 minus 2 times JIXB. Now this tip is the voltage of this potential of this lifted arm B. Now the potential difference, if you want, V1 and this is simply 2 JIXB. V2 and this is simply 2 JIXB, and V1 and this is this phasor actually. V1, you have to simply draw from V1 to this tip. So this is the phasor indicating the magnitude and direction of the voltage actually here and the phase of the voltage. So this is the difference in voltage between V1 and B. This is V1B. So this is how the voltage, these voltage differences are important for design purposes actually. So this is how the phasor diagrams of this changing the tap from one position to other position will appear like flag actually. That is why these diagrams are called flag diagrams, and the voltage drops are important in designing this one. And one more aspect here, when the half of the winding is there, what is the, suppose the full winding reactance is X, capital X, full winding reactance. The half winding reactance is here. What is happening here? No? So you are not changing the core. The core remains same. So simply N square by R, no? Inductance, N square by R. So simply number of turns is becoming half. So when you are using XB is therefore N square by R. R remains same. N square by reluctance. The N is becoming half. So it is simply X by 4 because it is square. So this you remember. It becomes X by 4. So these are the diagrams corresponding to inductive type or buffer type on-load tap changing. Next is resistive type. So resistive type is actually very simple. You can see here the construction of the resistive type OLTC. So in this case, you have two resistors here, R1 and R2. So here, there is a this conducting bar which is connecting these two positions here. In this case, entire current will flow through the dotted line here. So it will not flow through the resistor. It will flow like this actually directly. So through this I current is going to the line. Now next is in the next case, now we have to shift to from position 1 to position 2, say 1 1 2 2 2 we are moving. So in this case, what will happen? You can see here. So the case B is arm B is lifted simultaneously. But here you can see, so in the transition, so when this bar moves away from this point, then there is no connection, this direct connection. So the current has to move through the resistor R1. So then it connects here, but there is this B is still not connected, so there will be no current. And then in this case, when it exactly comes to the middle portion, so here the both 1 and 2 are connected here, but both are connected through these resistors. Normally these resistance values are chosen equal actually. R1 is nearly equal to R2. So this is the current here. But since 1 and 2 both are connected, so the voltage across this R1 and R2 is V12 actually. So that resistor voltage will cause a circulating current IC. So here this circulating current is in phase with the voltage, because these are resistors, these are not inductors. So the circulating current will flow from 2 to 1 in this fashion, 2 to 1. But the load current I by 2 will be shared equally by these two lines, and then total current I will come out. See, if you see each side, IA current is I by 2 minus IC, and this IB current is I by 2 plus IC. Now, in the final case, in the case D, so let us name here. This is A, case B, case C, case D, case E. Now, in case D, what is happening here is the arm A is also lifted, because this arm already touched B, and arm B already touched this tab 2. So arm A is lifted, and simultaneously this slab, this conducting slab is moving onto this terminal. So in this case, this is exactly symmetrical to case B actually. So V2 minus I2 R2 will be the voltage here. So in this case, finally, the arm 2 is also touching here, and this slab has moved up to this. So current will be flowing through this, and there is no resistor in loop actually. Through resistor, it won't flow. This is exactly symmetrical to case A. Now let us draw the phasor diagram, just like this. This is V1 phasor, and assume that this is position V1 phasor, and assume that this is theta, and this is I. Now V1 position, this is actually case A, corresponds to case A. Now case B, what is case B? In case B, the voltage at this node is simply V1 minus I R1. V1 minus I R1. So this is I. Now we have to find out this minus I R1. Minus I is in the opposite direction. So let me draw the phasor with a different color. So better to indicate this V1 and V2 the other side. So I will remove this, and here again pen. This is V1 and this is case A. So V1 minus IR1. Where is that V1 minus IR1? So that phasor. So V1 is here, minus I is in this direction. Therefore minus IR1. This is the case B position. The voltage is here at the tip of this one, minus IR. Now, in this case, where is this actually? So, in this case, You see, there is a circulating current also, but circulating current is in phase with V1 and V2, right? Why it is in phase with V1 and V2? Because this is resistors. So circulating current is IC, which is in phase with V1 and V2. So you can indicate circulating current like this somewhere, IC. Now I by 2. So now here you can go from anywhere to anywhere to obtain what is the position, the voltage in case C. Case C is a little bit tricky here. Now we can come from node A. Node A, this is node A voltage is V1. Node A means node 1, sorry. A and 1 are connected here, and B and 2 are connected also. V1 will start from V1 because V1 phasor is already there. V1 minus IA into R1 is the node voltage. Which node voltage? The line voltage actually. This voltage, this voltage, this voltage. V1 minus IA R1. What is IA? IA is given here. V1 minus I by 2 minus IC into R1, which is equal to V1 minus I by 2 into R1 plus IC into R1. R1 is simple scalar. So, V1 minus I by 2 into R1. Earlier we have this B position. Now this is V minus I R1. Therefore, V1 minus I R1, sorry. V1 minus I by 2 R1 is somewhere here, right? Somewhere here, middle, exactly, middle, I by 2 R1. And from here, you have to add IC R1. IC is here. IC R1 is also same, parallel to this one. Therefore, exactly parallel to B phasor. This is somewhere here. So, this is the new position, position B, position C, sorry, position C. So now your V2 will be somewhere here. So this is V2. Now you are here. What is the magnitude of this? This phasor, if I draw, this phasor is exactly I by 2 into R1. Minus I by 2 into R1, of course, magnitude I am drawing. So somewhere here in the middle, if it is V1 and V2 middle. So we have moved, the position has, this is A, this is B, this is C. So the same C can be obtained from V2 also. If you write from V2 side, it can be written as V2 minus IB into R1 is equal to V2 minus IB, I by 2 plus IC into R1. So equals to V2 minus I by 2 into R1 minus IC into R1. So simply from V2 also you have to minus I by 2 into R1, I by 2 into R2. So exactly similarly like this in this direction, I by 2 into R2, sorry, this is R2, here R2 will come. Already I told that R2 is chosen to be almost equal to R1. So minus IC into R2 will be like this. So from V2 also you can come, from V1 also you can come. So this is position A, position B, position C, and what is position D? So in this case, only B is connected, that is V2 minus IR2. Already we have drawn V2 minus I by 2 R2 is here. So V2 minus IR2 is simply double that one. So this is the position D. And then finally in E, there is no voltage drop because the 2 is directly connected. The voltage, the resistor is actually shunted here, means short circuited. So through resistor nothing will flow. So directly the terminal 2 is connected to the line. So you will end up in at E in V2. So now you can see this is also again a flag type diagram, right? Exactly. So now first you are here 1 A and here B and then C and then D and then E. So you can see this also looks like a flag only. So this is for a resistive type OLTC. The one difference you might have observed here, in position C, in the previous case, we were along the voltage phasor, but here it is a little bit different from voltage phasor. Okay, so this is the fundamental ways of connecting on-load tap changers, both resistive type and reactive type we have seen. So here again the voltages, when the these are lifting, right? So in this case very simple actually. It's not like reactive type. Reactive type is a little bit tricky because when there is no current also there will be some voltage in the reactance when the other portion is having the current, because the flux is linking this winding also, therefore induced EMF will be there. But in the case of this, in this case resistive type, no such complexity arises. Simply consider case B here, case B. In this one of them, that B is lifted, right? Now the voltage between B and 1 when it is lifted is of importance, because sparking etc. depends on this voltage difference between lifted arm and the approaching arm, or lifted arm and approaching tap, or lifted arm and leaving tap. So these voltages are important. These voltage drops are important. Now consider what is VB. VB is simply line voltage here, because there is no drop in this. Simply line voltage only we will get. So line voltage is V1 minus IR1. So the voltage between B and 1 is simply VB1 is simply IR1. So which is IR1? So this is the magnitude of IR1 actually. This is IR1. So again B and 2. Now B and 2 you have to indicate using this phasor actually. So this is the phasor. I'll draw with a different color. Red is already used. Let us use blue. So this is the difference between V2 and B. V2 and B. So this is the phasor. This is the phasor V2 B. And similarly, if you consider here, so this node potential VA in this case is exactly equals to line voltage because there is no current here in this R1. So this is same as V2 minus IR2. So where is it actually? So this is the V2 minus IR2 here. This is the node potential here. D, position D corresponding. Now the voltage between V1 and this and V2 and this is of importance. This voltage and this voltage is of importance. Now V2A and V1A is of importance. Let us see V2A. V2A is simply V2 minus IR2. So this is V2, this is V2 minus IR2. Therefore V2A is this magnitude only. This is simply IR2 is the difference. V2A is simply equals to IR2. But what is V1A? V1A, you can see, you have to do the phasor diagram here. So V1A, so node A is here at D only. So this phasor corresponds to V1A. Okay, so this is how we find out the voltages between moving arm and approaching tap or leaving tap, so which is important for design considerations. Thank you.